students, welcome back to 60 out of 60 in KCET Chemistry 2025 series in just 200 days. So now we are done with the PU1 chapters like some basic concepts of chemistry, structure of atom, classification of elements and periodicity in properties, and today we are going to start the fourth chapter, that is chemical bonding and molecular structure. Okay, so this is one of the most important topic from your PU1 series, okay, because you know PU1 carries very less weightage. So this is the chapter which is of high weightage from the PU1 series. So definitely please watch this complete series of chemical bonding, and we need like you can easily expect 2 to 3 questions from this particular chapter. Okay, so now one more request, you can join our WhatsApp channel, the link is there in the description section. So this will help you to get access to all your notes, to PDF notes, the mock test solutions, everything. Okay, so yes students, now let's see the next one, that is how are we going to complete this chapter. So this chapter will be completed in 3 parts. Okay, so in part 1, that is in today's lecture, we will be covering Kossel-Lewis structure, ionic bond and bond parameters. Okay, we'll be discussing all these 3 things in detail. Next, in part 2, we'll be discussing Vesper theory, VVT and hybridization. Now part 2 is going to be very important lecture because most of the questions are being asked from your Vesper theory and hybridization and from bond parameters. Okay, next in part 3 we'll be discussing MOT, that is molecular orbital theory, bonding in homonuclear diatomic molecules and hydrogen bond. Okay, so 3 lectures will be there. So today is the first class. Please sit with a notebook and pen and note down all the important things that we are going to discuss. Okay, at the end of the lecture we will also be practicing some previous year questions, and some questions have been taken from exemplar questions. Okay, fine. So now if you see the weightage, so in the past years you can see 1, 1, 1, 2, 3, then in the previous year 2017 to 19 it was continuously 2 questions are being asked. So I can say you can easily expect 1 to 2 questions from this particular chapter. Okay, 1 to 2 questions. Okay, so in part 1, that is in today's lecture, we are going to discuss Kossel-Lewis structure, ionic bond and bond parameters. Okay, and then in Kossel-Lewis structures we are going to discuss octet rule, covalent bond, Lewis representation of simple molecules, formal charge and limitations to octet rule. Okay, next in case of ionic bond we'll be discussing about lattice energy, and in bond parameters we have bond length, bond angle, bond enthalpy, bond order, resonance structures and polarity of bonds. Okay, so the basic many fundamental concepts we are going to discuss today, so please stay tuned for the complete class. So now the first part, that is Kossel-Lewis structure, what does it is actually? Okay, so now to define the chemical bonding among 2 elements or 2 atoms. So Lewis was the first person to come with a proposal about the chemical bonding of 2 atoms. So what exactly he said that? So Lewis postulated that atoms achieve the stable octet when they are linked by chemical bonds. Okay, so now the question arises, why the atoms has to form bond? Why can't they be isolated? They can stay with their own, why they want to combine with any other atom? So that was the first question. So this question was answered by saying that whenever an atom combines with another atom, it tries to get a noble gas configuration or it gets a stable electronic configuration. Now because the noble gases, we have studied in the last class that group 18 are the noble gases, right? Now because these noble gases are having 8 electrons in their valence shell, they are very stable and they do not participate in any bonding. But other elements also want to get that stability, so that is why they form bond with different elements to get that stability. So the first question is clear, why elements want to form chemical bonds? Okay, so Lewis said that they form chemical bonds to get that stable octet configuration. Octet configuration means in the valence shell there should be 8 electrons. Okay, that's the first thing. Next, the formation of a negative ion from a halogen atom and a positive ion from an alkyl atom is associated with the gain or loss of electrons by respective atoms. The negative and the positive ions thus formed attain stable noble gas configuration. The negative and the positive ions are stabilized by electrostatic attraction. So here he is saying one example, that so for example sodium chloride. Okay, if you take the example of sodium chloride, so sodium loses 1 electron, right? What is the electronic configuration of sodium? Sodium electronic configuration is 1s2 2s2, 2p6 and 3s1. So sodium loses this one electron to get Na plus. And why does it do that? So that it gains a stable configuration of 8 electrons in the valence shell. Similarly, if you see chlorine, so I'll write here chlorine, or let me write here, chlorine electronic configuration is 1s2, 2s2, 2p6, 3s2 and 3p5. Okay, now once it gain one electron, chlorine minus will be what? 1s2, 2s2, 2p6 and 3s2 and 3p6, right? Now because it is having now 8 electrons in the valence shell, it is stable, and that is why it wants to gain an electron. So sodium will lose an electron, chlorine will gain an electron. But what is the purpose of doing this? The purpose of doing this is getting a stable electronic configuration of 8 electrons in the valence shell. Okay. Now what Lewis also gave some Lewis symbols. Okay. So we'll discuss that now. So I'll clear this part. Okay. So how does he represented the elements? So he represented the elements with the symbols, okay, and these dots that you can see, okay, these dots represent the only valence electrons, okay. So in the Lewis structure, sorry, one second, in the Lewis structure, the dots represented what? Only the valence electrons. Okay. Now for example, if you see carbon electronic configuration is 1s2, 2s2 and so I can write 1s2, 2s2 and 2p2, right. So in the valence cell, that is in the last cell, second cell, there are 4 electrons. So these 4 electrons are only shown in the Lewis symbols. Okay. Now we will see how to use this Lewis symbol in a while. So now what is octet rule? So all of you would have understood by this. Octet rule says that according to this, atoms can combine either by transfer of valence electrons from one atom to another or by sharing of valence electron in order to have an octet in their valence shell. This is known as octet rule. So octet rule means that elements should have 8 electrons in their valence shell. Okay. Now to have these 8 electrons, they can follow 2 paths. Either they can lose or gain electrons, or they can share the electrons. Okay. So when they lose or gain electrons, we get an ionic bond, and when they share electrons, we get covalent bond. Okay. We'll study that in detail. Okay. Now coming to what is a covalent bond. When 2 atoms share one electron pair, they are said to join by a single covalent bond. Okay, if there are 2 atoms and there is sharing of electrons between them, okay, there is no transfer of electrons, there is just sharing of electrons, then we call it as a covalent bond. Now let us understand this ionic bond and covalent bond with a very simple example. Okay, now see, suppose ionic bond is there. Just let me take an example, very simple classroom example. Suppose you have a what I'll say, okay, in a class you got a project, okay, you just need to write some article or essay. The condition or the ma'am told you to write the topics in the blue pen and the content, the topics in the black pen and the content in the blue pen. Okay, so how you should write? Your essay should be like this. Okay, so here the topic should be there. Okay, so I'll just take any color. So topic should be there in some different color. Let it be black pen, and this, or you can say in violet pen, and this content should be in the blue pen. Right? This is what has to be done. Now you 2 friends are there. Okay, friend A and friend B is there. So there are 2 students A and B who are very good friends. Now what happens? How they will do this? So now in case of covalent bond, how we can explain that? See, suppose A is having only violet pen. Okay, okay, A is having violet pen and B is having blue pen. Okay, so now what they did, they decided that first A will write all the headings, okay, in the violet pen, then she will give the pen to B, and then B will write, at that time B will be writing the content part, okay, and after that B will give the blue pen to A so that he can write the content part, and the A will give the violet pen to B to write the topics. Okay, so in this way what they are doing, they all have 1 electrons, okay, or they have 1 pen, but they shared it with each other so that both of their projects are completed. When the projects came to ma'am, okay, she couldn't know at all that, okay, this blue pen was only with A and violet pen was only with A and blue pen was only with B. That didn't they didn't came to know that, right? So now that is what is called sharing of electrons. Okay, when you share electrons, that means it belongs to both, it is possessed by both the atoms, and these type of bonds are called as covalent bond. Okay, now I hope this covalent bond is clear to you. Now if we tell, okay, one second, okay, now suppose when these two atoms are held by one bond, okay, we call it single covalent bond. Example you can see here, suppose you see chlorine, okay. Now see, chlorine is having here 7 valence electron, this chlorine is having 7 valence electron, right. Now what they will do, they want both 8 electrons in their valence shell, they will share this 1 electron, right. These 2 electrons are shared, okay, one second. So these 2 electrons are shared. Now if these 2 electrons are shared, now these 2 electrons belong to this chlorine also and this chlorine also. So now this chlorine 1 will count 1, 2, 3, 4, 5, 6, 7, 8, and this chlorine will count 1, 2, 3, 4, 5, 6, 7, 8. So both their valence electrons are having 8 electrons, so their octet is satisfied, and that is why these 2 chlorines are forming bond. Now since there is only 1 electron pair, there is only one bond between them, it is a single covalent bond. Okay, now you can see another example here, CCl4. So if you see, carbon has only 4 valence electron, okay, and chlorine has, we know, 7 valence electron. So each carbon and each electron of carbon forms one bond with one chlorine. Okay, so you can see here all the bonds have been formed, and that is why you can see the chlorine octet is satisfied and carbon octet is also satisfied. Right. So this forms a single covalent bond. So you can see each of the 4 chlorine atoms along with the carbon atom again attains the octet of electrons. Okay. Now we will see what is double covalent bond. The 2 atoms are there. If in between them there is 2 covalent bonds, then we call it is double covalent bonds. Example is carbon dioxide. You can see carbon was having 1, 2, 3, 4 valence electron, right. Now oxygen gave its 2 electron. This oxygen also gave 2 electron. Oxygen octet is satisfied. Carbon octet is satisfied. So that is why here it is called CO2. Okay, double bonds in CO2 molecule. Now if you see the next one, that is when 2 atoms share 3 electron pair, they are said to be joined by a triple covalent bond. Now for nitrogen, if you see, we have 8 electrons, right. Now these 3 electrons are forming bond, here there is a bond formation. So this is why this is called as a triple covalent bond. Now if you see C2H2, so we have carbon, here hydrogen. So this carbon has 4 electrons, 1, 2, 3, 4, and 1 sharing with hydrogen, and this also gives 3 electron and 1 sharing with hydrogen. We get a structure like this. Okay, so these all are covalent bonds. There can be a double covalent bond, triple covalent bond, or single covalent bond between 2 atoms. Okay. Now coming to next thing, that is Lewis representation of simpler molecules. So these structures that we have drawn, right, we need to draw that. For that you need to follow certain rules that I can tell you now. So step number 1 is you have to count the total number of valence electrons. Step number 2 is for anions. So if suppose in the molecule there is some charge is given, like for example PO4 3-, so you need to add the number of electrons, and if it is a cation, for example NH4+, then you need to subtract the number of electrons. Okay, draw the skeletal structure. So in the skeletal structure, the least electronegative atom should be at the center. Okay, we'll do examples, it will be more clear. Now after accounting for the shared pair of electrons for single bonds, the remaining electrons are either utilized for multiple bonds or remain as lone pairs. The basic requirement being that each bonded atom gets an octet of electrons. So first we'll do the example, this will be more clear. We'll try for carbon monoxide, CO. Okay, so what is the step 1 is to count the total number of valence electron. So what is the total number of valence electron? So one second students. Yeah, so what is the total number of electrons here? Carbon has 4 valence electron, right? If you see 1s2, 2s2 and 2p2, right? So total in the second shell we have 4 electrons. Oxygen electronic configuration, if I write 1s2, 2s2 and 2p4, right? So oxygen has 6 valence electron, right? So what is the total number of valence electron? Total, I can write total valence electron is 6 plus 4, that is 10. Okay, 10 valence electrons are there. Okay, now what happens? The next step is to draw the skeletal structure. We'll draw this CO. Okay, now you need to do one bond between them. So if I draw one bond, so I have to use 2 electrons, right? So out of 10 I have used 2 electrons. Okay, now I need to see how many more electrons I can do. So I have 8 more electrons, right? Now these 8 more electrons, if I distribute like 1 2 3 4 1 2 3 4 1 2 3 4 5 6 7 8, right? Now if you see, if I draw like this, okay, can you see here? I've drawn here 2 electrons. I have given like this. Okay, so now is the octet satisfied here? For carbon, if you see 1 2 3 4 5 6 not satisfied, even for oxygen it is not satisfied. So what I can think is, I will do it like this. 1 second. Okay, so we have C and O, right? So I will do like this. I'll give total 10, there are 10 electrons, right? So I gave 6 electrons in between them. So 1 2 3 4 5 6, okay, 7 8 and 9 and 10 I gave like this. Okay, 9 and 10. Okay, so now if you see, the octet of carbon 1 2 3 4 5 6 7 8 is satisfied. Octet of oxygen 1 2 3 4 5 6 and 7 8 is satisfied, right? So now this one will give you both the carbon and oxygen are octets are satisfied. So this is the Lewis structure of CO molecule. Okay, now let us draw the structure for NO2 minus. Okay, so if you see that nitrogen has 5 valence electron, oxygen has 6, so 2 oxygen, so that is 6, and for this negative you need to add 1, so that is 18 electrons. Okay, 18 electrons are there. So now we need to draw the skeletal structure NO and O. Okay, so 1 second. Okay. So NO and O. Now if you see, if you draw the electrons here, so nitrogen has 5 valence electrons, okay, but with one positive, with one this extra electron I got 6 here, and here we have 6 electrons, and here we have 6 electrons. Okay, now how can we balance this? Now if you see, we can make here 2 bonds. Okay, so I will write this lone pair here. Okay, I will write this lone pair here. So you can see here like this. So now if I draw, and here I draw just one bond, suppose I use it like this. So we can make it like one bond is present in this. So we have here one and here one, and this is done. Okay, so now if I see I can remove one electron from here. So 1 2 3 4 5 6 7 8 1 2 3 4 5 6. Let us now draw the Lewis structure of NO2 minus. Okay, the step 1 is to calculate the total number of valence electrons. So nitrogen has 5 valence electrons, oxygen has 6. So 6 plus 6 12, because 2 oxygens are there, 12 plus 5 17. And here you need to keep remember that there is one minus charge. So you need to add this minus charge to the number of valence electrons. So 17 plus 1 18. So the total number of valence electron is 5 plus 6 plus 6 plus 1, that is 18. Okay, second step, what? We just need to draw the atoms, right? Now what we can do, we can just put one electron here, bonds I can do like this, and rest, so 4 electrons are used, the rest electrons I can just put as lone pair, right? So now I can put 1 2 3 4 5 6 7 8. Oxygen octet is satisfied. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18. Okay, 1 second. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16, and 2 more electrons are there, 17 18 I put. Now if I see like this, oxygen octet is satisfied, oxygen octet is satisfied. But if you see, nitrogen has only 6 valence electron, right, which is not satisfied. The octet is of nitrogen is not satisfied. Then how can we manage this? So what I can do is, we will bring these 2 electrons here. Okay, let me bring these 2 electrons. One second. So I will write like this. These 2 electrons I will bring here. Okay. So now if I see, for oxygen, 1 2 3 4 5 6 7 8 satisfied, 1 2 3 4 5 6 7 8 satisfied, here 1 2 3 4 5 6 7 8. Yes, all the elements are satisfied. So the structure will be like this. Okay, NO2 minus, and you can just draw the lone pairs here, and here we will get 2 and here we will get 3. Okay, clear? So that will be the structure of NO2 minus. Now let us go to the next question. What is formal charge? Okay, so formal charge, the definition you can understand, like in case of polyatomic ions, the net charge, suppose we wrote NO2 minus, so it is the charge of the complete NO2 ion, it is not the charge of nitrogen, oxygen or like that. So whenever we want to calculate the individual charge in a polyatomic system, that is called as formal charge. Okay, so formal charge of an atom in a polyatomic molecule or ion may be defined as the difference between the number of valence electrons of that atom in an isolated state and the number of electrons assigned to that atom in the Lewis structure. Okay, so just you can remember this formula. Formal charge is equal to Ne minus Ve minus Be by 2. What is Ne? So okay, so here a small change, here it is Ve minus Ne. Okay, so I'll write it down formula. What is Ve? V is valence bond electrons. Okay, Ne is non-bonding electrons. Okay, and Be is bonding electrons. Clear? Valence electron minus non-bonding electrons minus bonding electrons by 2. Okay, so now we'll do some calculation here. We'll do one example. Okay, let me erase this. Okay, so here I will write what are the meanings. So this is your Ve minus Ne. Okay, so what is Ve? Ve is valence electrons. Okay, then what is Ne? Ne is non-bonding electrons. Okay, and what is Be? That is bonding electrons. Okay, now we will calculate the formal charge of the questions that we have discussed in the previous. NO2 minus, right? What was the structure of NO2 minus? We did like this, negative charge here 2 electrons, and we have here 2 electrons, and here we have 6 electrons, right? This was the structure. If you can see, this is the structure, right? Yeah. So now we will calculate the formal charge of each of this atom. Okay, so let us start with the first. Suppose this is oxygen 1 and this is oxygen 2. So let us start with the first oxygen. Number of valence electrons. So total number of valence electron is 6 minus non-bonding electrons is 4 minus bonding electrons by 2. So if you see, bonding electrons are 1 2 3 4 4 by 2. So that is 6 minus 4 minus 2, that is equal to 0. So this oxygen formal charge is 0. Now if I want to calculate for nitrogen, valence electron is 5 minus non-bonding electrons is 2 minus bonding electrons is 1 2 3 4 5 6 by 2, right? So that is 5 minus 2 minus 3, and that is again 0, right? So nitrogen also has a formal charge of 0. Now oxygen, this oxygen O2 if I want to calculate. Okay, so I'm writing O1 and O2. Okay, this is not oxygen, O2 is the designation for this oxygen. Here if you see, the total valence electron is 6 minus non-bonding electrons is 1 2 3 4 5 6 minus number of bonding electrons by 2. So 2 is the bonding electron divided by 2, so we get minus 1. So this oxygen has a charge of -1, right? So if you add these all charges, you will get the total charge of the compound. Clear? Okay. Now we can go to octet rule and its limitations. So octet rule limitation is the incomplete octet of the central atom. So every compound does not have the octet rule. It cannot satisfy the octet rule. The example for this one of the example is your BCl3. Now if you see boron, okay, outer 1s2 and 2s2 and 3, the electronic configuration is 1s2, 2s2 and 2p1, right, for boron. So it has 3 valence electron, okay, and it forms bond with chlorine. 1 2 3 4 5 6 7 8, 1 2 3 4 5 6 7 and 8. Similarly here it is 1 2 3 4 5 6 and 7 8. So now if you see that chlorine octets are satisfied, but boron is having only 6 orbitals, 6 electrons, so its octet is not satisfied. So that is why every time the octet will be satisfied, that we cannot say. Okay, next one, odd electron molecules. Okay, so there are certain molecules which are having odd number of electrons, their 1 electron will be left as it is. Okay, so in that case also it is said that these odd electron molecules we could not explain it in a better way. Next you can see, okay, so this is odd electron molecule I have written 2 times. Here it is exceeds the, okay, let me use black pen, 1 second, yeah, so it is exceeds the octet rule. Okay, so here we have very good example of SF6. So if you see SF6, it has 6 electrons in the valence shell, 1 2, so I can write it in the 6 sides. Okay, yeah, so we have S 1 2 3 4 5, 1 2 3 4 5 and 6. So I will make it here one side 1. Okay, now if you have fluorine, okay, so 1 2 3 4 5 6 and 7. Similarly this side also 1 2 3 4 5 6 and 7. This side also 1 2 3 4 5 6 and 7, and 1 2 3 4 5 6 and 7. Here also 1 2 3 4 5 6 and 7. So you can see here this fluorine can form a bond. We have this fluorine forming a bond, this fluorine forming a bond. Here also there can be a bond formation, and so okay, 1 second, I'll do it neatly so that you can understand in a better way. Just a minute, we'll do it again. Okay, so sulfur has 6 valence electron, right? So I can draw it, sorry, 1 second, yeah. So if you see sulfur has, I will draw like this, okay, 1 2 3 4 5 and 6. Okay, so sulfur is here, fluorine is here, 6 electrons, 1 2 3 4 5 6 7 8 9 10 11 and 12, and these are fluorines 1 2 3 4 5 6 7, again 1 2 3 4 5 6, 1 2 3 4 5 6, 1 2 3 4 5 6, 1 2 3 4 5 6 and 1 2 3 4 5 6. Okay, so now if you see here, all the fluorines octet is satisfied, but sulfur is having 12 electrons in the valence shell, okay, which is more than 8 electrons. So there are certain compounds which even exceeds the octet rule. Okay, some compounds which are deficit of octet rule, some compounds which are more than the 8 electrons in the valence shell. And lastly, it does not explain anything about the shape and energy of the molecule. Okay, so now coming to the next thing, that is ionic bond. Okay, we just discuss what is covalent bond with the sharing of electrons. In ionic bond, what happens? The formed with the gain or loss of electrons. One compound will lose electron, another compound will gain the electron. Okay, so ionic bonds will be formed more easily between elements with comparatively low ionization enthalpy and high electron gain enthalpy. Okay, so now see, suppose A is losing electron. Okay, so we will get A plus plus electron, it is losing electron. Here the ionization enthalpy should be less, means very easily we should be able to remove an electron, and the one which is gaining electron, it should be very easily, it should gain an electron. If it is gaining electron easily, electron gain enthalpy will be more negative. If it is losing electron easily, its ionization enthalpy will be very less. So this type of combination elements will form very good ionic compounds. Okay. Now apart from in ionic compound, there is something called as lattice enthalpy. What is this lattice enthalpy? See, the lattice enthalpy of an ionic solid is defined as the energy required to separate 1 mole of solid ionic compound into gaseous constituent ions. So if I want to have like NaCl solid and you are giving some energy to separate Na plus gas and Cl minus gas. Okay, so when you break this molecule and you get the ions in the gaseous form, the energy required or the energy released in this process, okay, is called as lattice enthalpy. Or I can say when we have Na plus gas and Cl minus gas combining you to give you NaCl solid. Okay, so this is also called as lattice enthalpy, and in this case what will happen, energy will be released. Okay, and this is also lattice enthalpy, but in this case what we can say is energy required when you are breaking it. Okay, these two values will be same but the signs will be different. Okay, that is called as lattice energy. When you have finally the gaseous ions, when they combine, they release a lot of energy, that is called as lattice energy. Or when you break a ionic solid to its gaseous constituent ions, that is also called as lattice energy. Okay, fine. So now we will move towards bond parameters. Okay, this is very important. So first thing we'll understand is bond length. Okay, so what is bond length? Bond length is defined as the equilibrium distance between the nuclei of two bonded atoms in a molecule. Two bonded atoms are there, suppose A and B have bounded. Okay, so just if I give an example, A and B. Okay, so here they are forming a bond, so the distance between the nucleus of A and B is called as bond length. Okay, now there are different types of radius that can be explained. One is covalent radius, another is van der Waals radius. Okay, slight differences there in their definition, you need to understand it carefully. Now see, the covalent radius is measured approximately as the radius of an atom's core which is in contact with the core of an adjacent atom in a bonded situation. Okay, now this is very important. See, the covalent radius is the half of the distance between the two similar atoms joined by a covalent bond. When two similar atoms are joined by a covalent bond, the distance between their the half of their distance is called as your covalent radius. Now what is van der Waals radius? Now see, van der Waals radius represents the overall size of the atom. Okay, what is covalent radius? Is the radius of an atom's core. Okay, just the atom nucleus, atom's core. Okay, but van der Waals radius tells you the overall size of the atom, which includes its valence shell in a non-bonded situation. Okay, you can understand, when it is in non-bonded situation, the overall size of an atom is called as van der Waals radius. Covalent radius is calculated when the atom is in a bonded situation. Okay, the difference you are getting, covalent radius can be calculated when it is in a bonded situation. Van der Waals radius is the overall size of the atom when it is in non-bonded situation. Okay, how to measure van der Waals radius? The van der Waals radius is half of the distance between two similar atoms in a separate molecule in a solid. Okay, this is very important. I'll explain you with an example. Now see, these are two chlorine molecules that has formed bond. Okay, now the distance between the core of this chlorine and this chlorine is 198 picometer. Okay, now half of this distance is your 99 picometer, and this is called as covalent radius. Why? Because here we have considered two bonded atoms. Okay, now if you see, this is one chlorine molecule, this is another chlorine molecule. Okay, now the distance between the nucleus of this one and this one, this chlorine and this chlorine, which is not bonded. Okay, these two chlorines are not bonded. Now this distance is 360 picometer, and then if you take a half of this, it is 180 picometer. So this distance 180 picometer, which tells you about the overall size of the atom, is called as your van der Waals radius. Okay, covalent radius, when two atoms are forming bond and you take a distance between, measure their distance between the core and take half of it. Van der Waals radius, two non-bonding atoms, there is no bond between them, you measure their distance and take half of it. Okay, so in the, you can see here, in covalent radius only the core of the atom is considered, but in van der Waals radius the valence shell is also considered. Okay, the overall size of the atom is given by the van der Waals radius. Clear? I hope this diagram is very clear to all of you. Okay. Next we'll go bond angle. So what is bond angle? It is defined as the angle between the orbitals containing the bond electron pairs around the central atom. Okay. Now bond angle is expressed in degree. So you can see, suppose this is the compound shape, the bond between or the angle between the bond pairs of an atom is called as bond angle. Okay. Next bond parameter is bond enthalpy. So it is defined as the amount of energy required to break 1 mole of bond of a particular type between two atoms in a gaseous state. So when you are giving some energy to break a particular type of atom, whatever energy is required, that is called as bond enthalpy. Okay. The unit of bond enthalpy is kilojoule per mole. So that if the, now this is very important, if the bond dissociation energy is larger, okay, you want to give more energy or you have to give more energy to break a bond, that concludes that that bond is very strong. Okay, so that stronger will be the bond. Okay, if you are giving more energy, more bond is required, more energy is required to break a bond, that implies that the bond is very strong. Okay, next we have bond order. So bond order is given by the number of bonds between the two atoms in a molecule, number of bonds. Okay, now for example, if you see so for example, if I say O2, this is the structure of O2, this is the structure of N2, this is the structure of H2, right? So here between two atoms number of bond is 2, here 3, it is 1. So the bond order are 2, 3 and 1. Now the isoelectronic molecules and ions have identical bond orders. For example, F2 and O2 2-. So if you see F2 and O2 2-. So the total electrons here is 9 plus 9 18, and here it is 68 plus 8 16 plus 2 18, right? Now these, if there are 18 electrons, these are isoelectronic species, then we can say that their bond order will also be same. So both of them have bond order of 1. Now if you compare N2CO and NO plus, N2CO and NO plus. So N2 has 14 electrons total, 7 plus 7, carbon 8 plus 6, 14, here 7 and here 8, 7 plus 8 15 minus 1 14, right? So they all will have a bond order same, that is 3. Okay. So next one, with the increase in bond order, so if there is more bond order, means here if you see there is more bond order, okay, with the increase in bond order the bond enthalpy increases. So more is the bond order, you need to give more energy to break that bond. Okay, so bond enthalpy will increase and bond length will decrease. Okay, so always remember bond length, okay, is inversely proportional to bond strength. Okay, stronger, if the bond is very strong, the length will be small. Okay, if the bond is very weak, then length will be bigger. Now how can you remember this? See, if you have a bundle, okay, or two sticks, just imagine two sticks are bounded to each other and this much lengthy stick is given to you. You can easily break it, but imagine the same thing, you have two sticks, okay, but this much small size. Can you break it easily? No, right? It is very difficult to break small things. So you can understand when you require more energy to break that, the size will be small. When it is very big, lengthy, then you can easily break it. Okay, I hope you can remember this one in this way. So this is all about bond order. Next, coming to resonance. So why the concept of resonance is there? Now there were certain structures, okay, which could be like the Lewis structure can, like the same, we can have 2 or 3 different structures for that particular same molecule. Okay, so in certain cases of this, where you can have more than one Lewis structures for one particular compound, we call that they have resonance. Okay, so what does this say? According to the concept of resonance, whenever a single Lewis structure cannot describe a molecule accurately, you cannot have only one Lewis structure for that particular molecule. A few structures with similar energy, position of nuclei, bonding and non-bonding pairs of electrons are taken as the canonical structures of the hybrid, which describes the molecule accurately. Okay, so we will understand this with the help of an example. Okay. Now you can see ozone molecule here. Okay. So we have oxygen. This one is the ozone molecule. Now we can have, this is one structure and this is another structure, right? You have two different type of structures for ozone. Now this is also correct, this is also correct, then which is the best one? So that is why what happens in such cases, for such molecules there is a concept of resonance. So the structure of these molecule will be, so these structures are called as canonical structures, and combination of these two structures is this one, where you just represent this double bond with dotted lines. That means the double bond can be present here also, can be present here also. Now this structure is called as your a resonance hybrid. Hybrid is the combination of the canonical structures. Okay. So if somebody asks you what is the structure of the ozone, you need to draw this diagram. Okay. That is the actual structure of ozone. Okay. So resonance hybrid concept is there whenever you do not have a single Lewis structure for a particular compound. So we combine all the canonical structures to give one structure, that is resonance hybrid. Okay. So energy of resonance hybrid is less than the canonical structures. This is very important. If you compare the energies, so resonance hybrid energy will be less than the canonical structures. Okay. So that's all about this. Next we'll go for the doing resonating structures of these two compounds. Okay. First let us try with CO3 2-. I calculate the number of valence electron. Carbon has 4 valence electron, sorry. Yeah, carbon has 4 valence electron, oxygen is having 6, so 6 3s are 18 plus 2, right? 24 electrons are there. Calculation is correct. 6 3s are 18, 19, 20 plus 4, 24. Okay. So I can write total valence electron is 24. Okay. Now carbon is the least electronegative atom, so I'll put 3 oxygens along the carbon. Okay. Now I'll give one bond here, one bond here, and one bond here. Okay. Now if I see, I have used 1 2 3 4 5 6, but carbon octet is not satisfied, so I'll put one more bond here to satisfy the octet of carbon. Now 1 2 3 4 5 6 7 8. Okay. 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 24. Now you see octet of all the atoms are satisfied, 1 2 3 4 5 6 7 8. Yes, this is done. Okay. Yeah. Now one second, you can see here 1 2 3 4 5 6 7 8, 1 2 3 4 5 6 7 8, 1 2 3 4 5 6 7 8. So all the octet is satisfied. Now this is one form. We can have, so resonating hybrids are shown with a double arrow. We can have a structure like this as well, right? And one more structure like this. Okay. The lone pairs I am not doing, so you can show here like this. Okay. So this 3 structures are possible. Then how will we draw the resonance hybrid? So it is like this. The resonance hybrid will be clear. So this is the resonance hybrid of CO3 2-. Got it? Now if you see CO2, so here also 4 plus 6 plus 4, 6, right? So we have 16 valence electron, 6 plus 4 10 plus 16. So here we have oxygen and oxygen. So let me draw it like this. Okay, so we have C double bond O and double bond O. Now what I can do, I'll do 1 electron here. So 1 2 3 4. Then to satisfy the octet, 5 6 7 8. Now 9 10 11 12 13 14 15 16. Okay. Now 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. Yeah, 16 valence electrons are done. Okay, all the electrons are given, all the octet is satisfied. Now there can be another possibility, resonating structure like this, where I can draw the structure like this. Okay, you will see that still the octet will be satisfied here. So I can say that 1 second. Okay. Yeah. Now check 1 2 3 4 5 6 7 8, 1 2 3 4 5 6 7 8, 1 2 3 4 5 6 7 8. So this also molecule is having an structure where the octet is satisfied. Okay. So these two structures are possible. Okay. So the resonating, these are the canonical structures of CO2. Got it? Now we'll come to the next topic, that is polarity of the bonds. So this is very important. See, now in a compound, no bond, so we have discussed that there are two types of bond. If a bond is formed by sharing of electrons, we call it covalent bond. If a bond is formed by the transfer of electrons, that is either by losing or by gaining electrons, we call it ionic bond, right? So but there is one very important thing, that no bond of a compound is either completely covalent or completely ionic. Okay, there is always some mixture of the bond is always present. Now how can we tell that? First we will understand the ionic nature in covalent bond. First we will understand ionic nature in covalent bonds. Okay, now what happens, suppose let us take the example of H2. Okay, H2 bond is like this. Okay, here this bond we can say that it is, there is no separation of charge, nothing, so we can, there is no polarity here, we can say this is a non-polar bond. But if I consider HCl, okay, now these electrons are present, but we know that chlorine is more electronegative than hydrogen. Then what will happen, these electrons will be more attracted towards the chlorine. Okay, so they will shift towards the chlorine. Okay, so these electrons will shift towards chlorine. So here we'll get a slight negative charge and here we'll get a slight positive charge, right? So an ionic character is developed in this type of bond. So these type of bonds are called as polar bonds. Okay, now this polar bond is represented or is termed as like dipole moment. Okay, so what is it? Now see, dipole moment is the dipole moment. Okay, dipole moment given by the symbol mu is charge into distance. Okay, it's a vector quantity and it is given by the charge and the distance between the two points. Now we represent dipole moment with an arrow and a crossed arrow. Okay, the head of the arrow should be towards the more electronegative atom. Okay, now these dipole moments, the direction of these dipole moments will tell you whether the compound is polar or non-polar. Okay, now let us take the example of BeF2. Okay, so if you see BeF2 structure is like this. Okay, now what happens, fluorine is more electronegative, so the electrons will shift this side, so we will get a dipole moment here, and this fluorine is more electronegative, so we will get a dipole moment on this side. So because the dipole moments are in two different directions, okay, opposite directions, and this is a vector quantity, so addition of two equal and opposite vectors in opposite direction will give you a net dipole moment of 0. So now there is no dipole moment in this particular molecule. These bonds are definitely polar, but there is no net dipole moment. That is why we can say that BeF2 is a non-polar molecule. Why? Because the net dipole moment is 0. Here we can say it is polar, okay, because it has some net dipole moment, and here it is non-polar because there is no dipole moment at all. Now if you see BeF3, okay, if I draw the structure of BeF3, it is like this. Okay, now in BeF3 what happens, we get the dipole moments like this. Okay, now these two, as we say, dipole moment is a vector quantity, these two vectors add up to give a vector in this direction. Okay, so again this vector and this vector gets cancelled up, the net dipole moment becomes 0, and that is why we can say that BeF3 is also non-polar. Okay, now if you see CO2, okay, if I draw CO2, okay, so this has a vector dipole moment on this side and this has a dipole moment on this side, right? Now again, because oxygen is more electronegative than carbon, again the two dipole moments are equal in magnitude and opposite in direction, so they cancel out each other. Net dipole moment of the molecule is 0. If net dipole moment is 0, then again we can say that CO2 is a non-polar molecule. One second. Yeah, CO2 is a non-polar molecule. Okay, now if we compare about NF3 and NH3, okay, so NF3 and NH3 both are polar molecules, but here a question arises, which one is more polar? Okay, so that we will see in the next slide. Okay, I will use this place, where can I write? One second. Okay, I can erase this part. we can use this piece. 1 second. Yeah, I hope you have noted down what is dipole moment. Okay, so I am erasing this one and I'll use this space for explaining this one. Okay, 1 second. Okay, so just now whatever I wrote, I'll write here. Dipole moment. Okay, dipole moment is equal to, given by the symbol mu, is equal to charge into distance. Okay, now we'll come to NH3 and NF3. Now if you draw the structure of NF3, it is like this. Okay, and if you draw the structure of NH3, this is like this. Okay, now what happens, if you see in NF3, fluorine is more electronegative, so the dipole moments are in this direction. And lone pair, always remember, whenever there is a lone pair, the dipole moment will be towards the lone pair. Okay, so now what happens, there will be a net dipole moment on this side. Okay, this is, I'll do it in the different color. The net dipole moment, the net dipole moment and this dipole moment gets cancelled out, some amount gets cancelled out, overall not zero, okay, but there is some cancellation, because of which the dipole moment is less, okay, because of cancellation. But if you see here, the dipole moments directions are like this side, and again this side and this side, right, because nitrogen is more electronegative. So what happens, this will have a resultant dipole moment, right, so this will have a resultant dipole moment and this lone pair dipole moment are on the same direction. So what happens here, the dipole moments adds up, okay, but here what happens, the dipole moment subtracts. Now because of this, what happens, there is, even the fluorine is more electronegative, but due to the vector addition, we can say all the dipole moments are in same direction. NH3 is more polar than NF3. Okay, so what I can write here, NH3 is more polar. Okay, clear? Fine. So that is there. Next we will understand that just this is what we understood in covalent bond, how the ionic character gets developed, okay, in covalent bond. But also similarly in ionic bond there will be also a partial covalent character, okay, and this is told by your Fajan's rule. According to Fajan's rule, we can discuss or we can decide how much covalent character is there, how much covalent character is present in any ionic bond. How to decide that? Here are some rules. See, though in an ionic compound there will be a cation and anion. So the smaller the size of the cation and larger the size of the anion, the greater is the covalent character of an ionic bond. Okay, so for covalent character we need smaller cation and larger anion. Okay, next one, the greater the charge of the cation, the greater covalent character of the ionic bond. So second thing is about the charge of the ion. Okay, if the cation is having more charge, then also it will be covalent in nature. Third one, for cations of the same size and charge. So suppose cation is also size of the, so suppose for example you have like this, A plus B minus, A plus C minus. Okay, or let me take something, 1 second. Okay, so D plus and C minus, but A and D are having same charge and same size, then how will you decide? So for cations of same size and charge, the one, okay, the one with electronic configuration of transition elements or transition metals is more polarizing than the one with a noble gas configuration typical of alkali metals and alkali earth metal cations. Okay, so that is what saying, suppose A and D both are cations and have same size and same charge, then how will you decide which is more covalent in nature? So the one, if any of this is belonging to transition elements, okay, that means belonging to D block, that will be more covalent in nature. Okay, that is the third point. Next we have the polarizing power of the cation, the polarizing power of the cation, the polarizability of the anion and the extent of distortion of the anion are the factors which determine the percentage of covalent character in the ionic bond. So now here one very important thing, we just discussed how in a covalent bond the ionic nature comes, right? That is because of, so why in covalent nature the ionic bond comes, that is because of this like suppose if I have HF, because fluorine is more electronegative, electron shifts here, delta minus delta plus is formed, and that is the reason of the covalent that is the reason of the ionic nature in covalent bond, right? Then what is the condition, what is the reason for the covalent nature in ionic bond? Okay, so that is we will discuss here. Just a minute, I'll use this space. Now see, you have a cation, okay, and you have one anion, yeah, and you have a anion. So now what happens, this cation and the anion, this cation can pull this anion towards itself, so the electron cloud present here, okay, gets distorted like this. This is suppose plus, and yeah, this minus charge is getting distorted, okay, and this is called as when this type of, now what happens, there is a overlapping here, this plus charge and this minus charge is overlapping here, and this results in the covalent nature, right? So that is what is the last point here, the polarizing power of the cation. The cation should be able to polarize the anion, right? This what is polarizability, this one is called as polarizability, okay. So the polarizing power of the cation will depend on the size of the cation and charge of the cation. Size should be small, charge should be more. The polarizability of the anion should also get polarized, it should also have the tendency to get polarized, and the extent of the distortion, polarization of anion, how much it is getting distorted, how much polarization is taking place on the anion, are the factors which determine the percent covalent character of the ionic bond, okay. So that is all about the topics that we are going to discuss today. So now it's time to do some practice questions, okay. I hope you have understood all the concepts. Let us do some questions practice. The formal charge on the central atom of the ozone. So if you remember, ozone structure was like this, right? Okay, we will draw it, okay. Okay, let us see. Ozone is O3. O3, right? So what is the total valence electrons? You can see 6 plus 3, we have 18 valence electron, right? Because each oxygen is having 6 valence electron. So now I will draw all the 3 oxygen like this. I'll put 1 bond like this, right? So 1 2 3 4. Then I can balance it like this, 5 6 and 7 8, okay. Now if you see this oxygen 1 2 3 4 5 6 and 7 8, 1 2 3 4 5 6 and 7 8. Now if you calculate that, is the octet satisfied? 1 2 3 4 5 6 7 8, yes. 1 2 3 4 5 6 7 8, yes. 1 2 3 4 5 6 7 8, yes, right? So now we need to calculate the formal charge of this central atom, okay. You need to calculate the formal charge of the central atom. So now if I see, the total valence electron is how much? 1 2, oxygen total valence electron is 6. The non-bonding electrons are 2, right? Minus bonding electrons by half. So bonding electrons are 1 2 3 4 5 6. So 6 by 2, right? So now if you calculate 6 minus 2 minus 3, so that is plus 1, right? So the correct answer for this question will be option number C here. Next, which of the following possess net dipole moment? So I have shown you BF3 will not have, BeCl2 will not have, CO2 will not have, SO2, if you see the structure of SO2 is like this, okay. So that is why here there is a net dipole moment, and that is why there is some not exactly cancel out, but yes, the molecule is polar, so option number A. But in BF3, BCl2 and CO2, if you see the structure of BF3, it is like this, okay. So the resultant and these two dipole moments cancel out exactly, and if you see BeCl2, it is like this, right? So the dipole moment will cancel it out, so non-polar. Similarly, CO2 molecule is also, the structure is like this, it is like this, C, okay, clear? Next, which of the following pairs contain 2 lone pairs of electron on the central atom? Okay, in the central atom there should be 2 lone pairs. So if you see NF3 structure, okay, nitrogen has 5 and fluorine has how much? 7, so 21, so total 26. Nitrogen has 5 valence electron, fluorine has 7, so 7 into 3 21, 21 plus 5 26, right? So if I now write this 26 electron structure, okay, I'll draw it for NF3. NF3, So we can first draw like this, 26, right? So I have used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So if you see, this is the structure of NF3 and on the central atom we have only one lone pair. So this is not the answer, we can eliminate this one. Now if you see NH3, NH3 is 5 plus 3, it has 8, right? In NH3 there are 8 valence electron. So I'll first draw like this, 1, 2, 3, 4, 5, 6 and again 7, 8. It is also having only one lone pair, so we can eliminate this one. Now if you see here, SO4 2 minus, H2S and SO4 2 minus. So let us draw for SO4 2 minus. So sulfur is having 6, 7, 8, right? So sulfur has 6 valence electron. So 6 plus oxygen is also 6. So 6 into 4, 24 plus this 2, right? So we will get 24, 25, 26 plus 6, 32 electrons are there. Okay. So let us do first, there are 4 oxygen. So we can draw like this, that, okay. 1, 2, 3, 4, 5 and 6. Right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Okay. So now you see in the sulfur there is not even a single lone pair is present. So that is why this is also the wrong answer. So this has to be the correct answer. Now if you see the structure of oxygen, oxygen has 6 valence electrons. So each will form bond with hydrogen, right? So 1, 2, 3, 4. Total valence electron is 8, right? 1, 2, 3, 4, 5, 6, 7, 8. So that is correct. I3 plus. So if you see, I is having 7 valence electron. 7 into 3, 21, but there is 1 plus charge, so 21 minus 1 is 20. So in I3 plus there is 20 electrons. So how can I draw that? So let me erase this one. So SO4 is having 32 valence electron and here it is 20. So I will draw like this, another I and another I. So now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So there are, you can see on the central atom 2 valence electrons are present. So that is why this is the correct answer. Okay. Now let us see the next question. Which of the following is the correct electron dot structure of N2O molecule? Okay. So for electron dot structure, the first criteria is that the octet rule should be satisfied. Now if you see here 1, 2, 3, 4, 5, 6, only 6 electrons, octet is not satisfied, so this is the wrong answer. Similarly, if you see 1, 2, 3, 4, 5, 6, octet is not satisfied, you can eliminate this option. Here if you see all the atoms octet is satisfied, here also it is satisfied. Okay. Now what we can do to decide this, we will calculate the formal charge of all the atoms present in this structure. Okay. So first let us take option number A. Okay. What is option number A? We have N, double bond N, then you have double bond oxygen, and we have 2 electrons and 4 electrons like this and 4 electrons like this. Okay. Now you need to just calculate the formal charge on this one. So for this first nitrogen, okay, so if I write N1 and N2, so for N1, okay, so total number of valence electron is 5, number of non-bonding electrons is 4, and number of bonding electrons 1, 2, 3, 4 by 2, right? So that is 5 minus 4 minus 2. So this will give you minus 1. Okay. Now if you calculate N2, that is again 5 valence electrons are there, then 0 non-bonding electrons 1, 2, 3, 4, 5, 6, 7, 8 by 2. Okay. So this is plus 1. So here we got next oxygen we have. Formal charge is total valence electron is 6, right? Bonding electrons, non-bonding electrons are 4, and then 1, 2, 3, 4 by 2, right? So this is giving you 0 charge. So what are the formal charges that we have calculated? For N1 it is minus 1, it is plus 1, and this is 0. Now let us do the option number B calculation. Okay. For option number B we have N, triple bond N plus O minus. I will not write plus and minus, I will just write the atoms. Okay. So here, and then we have 1, 2, 3, 4 and 5, 6. okay, and here we have, so this is suppose nitrogen 1 and this is nitrogen 2. So N1, if I want to calculate the formal charge, how much it will be? Valence electron is 5, non-bonding electrons is 2, then this is 6 by 2. So here we will get 0. If I want to calculate N2, okay, so total valence electron is 5, non-bonding electrons is 0 and bonding electrons is 1, 2, 3, 4, 5, 6, 7, 8 by 2. So that is your plus 1. Now if I want to calculate for this oxygen, okay, so total valence electron is 6, non-bonding electrons is 6 and bonding electrons is 2 by 2 and that is minus 1. So we get what are the formal charges that we are getting here. So I can write the formal charges in a different color. So this is your 0, this is plus 1 and this is minus 1. Okay. So now if you compare, so we will just write down the formal charges this side. So that is we have N, first one, N, oxygen, and here I have these charges and here I have these charges. And the second structure is like this, triple bond, N, and then oxygen, and we have 6 bonds. Now if you see the charges here, right, so this is minus 1, this is plus 1, this is 0, and in this case this is 0, this is plus 1 and this is minus 1, right. So these two structures seems to be very same in the basis of charge and all, but the question here arises is where should be the negative charge more stable. You should always remember that negative charge is more stable on more electronegative atoms. Okay, so if I see here oxygen is more electronegative, okay, so that is why this negative charge on oxygen is more stable. So that is why, which is the correct structure? Option number D is the correct structure. Okay. Next, question number 5, HCl gas is covalent and NaCl is an ionic compound. This is because sodium is highly electropositive, hydrogen is a non-metal, HCl is a gas, electronegativity difference between the hydrogen and chlorine is less than 2.1. Okay. So now this is because the electronegativity difference between HCl should be less than 2.1. Okay. If the electronegativity difference is less than 2.1, then we get a covalent compound, otherwise we will get a ionic compound. Okay. Next, question number 6 is taken from your exemplar. Which of the following has the highest dipole moment? Okay. So CO2 is not a dipole moment, we have just discussed. Now if you see in case of H2O and SO2, the structure of H2O is like this and the structure of SO2 is like this. Okay. Now sorry, 1, 2, 3, 4, there is only one lone pair. Now what happens, because of more electronegativity of oxygen, oxygen is more electronegative, we know dipole moment formula is what? Q into D, right? This Q value should be considered, that is the charge. So because of more electronegativity nature of oxygen, H2O is the most dipole moment or having highest dipole moment here. Okay, and in HI there is no much I value, is Q value is very less. Next, coming to 7th question, in PO4 3-, the formal charge on the oxygen atom of PO bond is. So if you draw PO4 3- structure, okay, so let us first do phosphorus is having 5 valence electron, oxygen is having 6 into 4 24, and then we have 3, right. So 24 plus 3 27, 27 plus 5 is 32. So if I draw this one, phosphorus, oxygen, we have 4 oxygen, right. So 32, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, right. This is the structure. Now in PO4 3-, the formal charge on the oxygen atom of PO bond, okay, you need to calculate the formal charge of any of this one oxygen atom. Number of valence electron is 6, non-bonding electron is 6, bonding electrons is 2, divided by 2, that is minus 1, right. So correct answer is option number B here. Next is this a homework question. In NO3-, the number of bond pairs and lone pairs of electron on nitrogen atom are. So first of all you need to draw the structure and then you need to calculate the number of bond pairs and lone pairs. Okay. So yes students, this was the first part of chemical bonding. Tomorrow's in the next class we are going to discuss very important topic, that is Westward theory. So please stay tuned for tomorrow's class, and yes, if you have enjoyed today's class, do not forget to subscribe the channel and join our WhatsApp channel for all these notes and mock tests. Okay, thank you once again and see you soon in the next episode.